Have you ever stopped to think about how we can possibly see the invisible forces of air flowing over a jet wing before it's ever built? Or, how meteorologists can even begin to predict the path of a massive hurricane? It all comes down to the unseen world of fluids, the air, the water, that's constantly shaping our lives and all our technology. Today, we're going to pull back the curtain on the incredible tool that makes it all possible.
So, here's our game plan. We'll start with what CFD actually is, take a quick trip through its history, and then break down how it works. After that, we'll get into all the real-world applications, talk about its limits, and, finally, peek into what the future holds.
All right, first things first. What in the world is computational fluid dynamics? Or, as everyone calls it, CFD.
Think about it. This is the fundamental problem, right? We are completely surrounded by fluid dynamics, but almost all of it is totally invisible. How do you study something you can't even see? For decades, the only answer was to build really expensive and sometimes pretty dangerous physical models. But then, a whole new way of thinking came along.
And here it is. At its very core, CFD is like a digital laboratory. It uses incredibly powerful computers to simulate or mimic how fluids behave. So instead of building a physical car and sticking it in a giant wind tunnel, you build a digital car and run it through a virtual one right on your computer.
Now, a tool this powerful didn't just appear out of thin air. Its story is completely intertwined with the rise of the computer itself.
This timeline just lays it all out, doesn't it? You can literally see how CFD's progress was strapped to a rocket powered by Moore's Law. It started as pure theory in the 50s, then in the 70s it became this super specialized tool for giant mainframe computers. By the 80s, we could actually simulate flow around entire airplanes. Then things got really interesting, as the focus shifted to the super complex Navier-Stokes equations, which, that's the code for how fluids really behave. Ever since the 90s, as computers got cheaper and way more powerful, CFD has become a standard, must-have tool in pretty much every field of engineering.
Okay, so how does a computer actually see a fluid? It's not magic. It's really just a three-step process that turns a real-world problem into a math problem a computer can actually solve.
First, you define your geometry. Could be a car, an airplane wing, maybe even a human artery. That whole space is your computational domain. Second, you chop that domain up into a digital grid or mesh made of thousands or even millions of tiny little cells. And finally, the computer just gets to work, solving the fundamental equations of physics for every single one of those cells, over and over and over until the answer makes sense.
Now here's the crucial part. CFD isn't just making educated guesses. It is crunching the numbers on the fundamental laws of physics that govern the real world. We're talking about equations like the Navier-Stokes equations, which are basically the fluid version of F equals ma. By applying these hardcore physics laws to that digital mesh, the computer spits out this massive set of numbers that is, essentially, a snapshot of how the fluid is behaving.
Okay, so that's the how. Now for the really cool part. Let's look at the absolutely incredible range of ways CFD shows up in our actual everyday lives.
The impact is just staggering. It's used to design quieter, more fuel-efficient cars and planes. In medicine, it's helping us understand blood flow to design better artery stents. In architecture, it makes sure that our tallest skyscrapers can handle crazy high winds. It is a cornerstone of modern weather forecasting. Seriously, from designing jet engines to cooling the tiny microchips in your phone, CFD is absolutely everywhere.
And this quote, this just nails why CFD is such a game changer. In the real world, everything is connected, right? You've got heat, turbulence, chemical reactions, all happening at once. CFD lets engineers model all of these complex things at the same time, giving them this holistic, big-picture view that was just impossible before.
But, as powerful as it is, CFD isn't magic. It's a simulation. And that means it has both incredible strengths and some really important limitations.
So let's put it head-to-head with old-school methods like wind tunnels. For one, CFD is often way cheaper and faster. You can test 100 different digital designs for the cost of building one physical prototype. You can also simulate really dangerous things, like an explosion or a fire, without putting anyone in harm's way. And maybe best of all, a simulation gives you data for every single point in your model, a level of detail you could never get with physical sensors.
But, and this is a really big but, it's so important to stay grounded. The experts in this field are the first to tell you that CFD is far from a solved problem. The physics underneath it all are just ridiculously complex, and our ability to model them perfectly is, it's still a work in progress.
These right here are some of the big frontiers. Turbulence, for instance, is one of the great unsolved mysteries in classical physics. So yeah,
Modeling it accurately is a huge challenge. And simulating something like the complex combustion happening inside a jet engine or dealing with extreme heat transfer, these are all areas where researchers are working like crazy to push the boundaries.
So, where is all this headed? Well, as computers just keep getting exponentially more powerful, the future for CFD looks incredibly exciting.
I love this quote. It's from 1955, before CFD was even really a thing, and it just perfectly captures the spirit of this whole field. The goal isn't just to generate mountains of data. It's to gain a deeper understanding, to get real insight into how our world actually works. And that kind of leaves us with one last big thought. As our computing power continues to just explode, what new doors are going to open? Will we be able to simulate an entire human circulatory system in real time? Create climate models with an accuracy we can't even dream of today? Or maybe design totally revolutionary new forms of clean energy? With CFD, we're getting closer and closer to making the invisible completely visible.